So let's go ahead and get started. And so in the simplest schemes, well, I shouldn't say the simplest, we're going to actually talk about one that's even more simple than this, but typically the way that this is set up is we have, remember, enzymes are just biological catalysts. That means they're not consumed during the process, and so you're going to get them back. So you have a binding event. You're going to get something which is called the ES complex, or sometimes they also refer to it as the Michaelis complex. That'll make more sense after we go over Michaelis-Menten. Then you can get catalysis, where the product is still bound, and then ultimately you get enzyme and product. Each step is going to have its own transition state and its own energy minima, okay? Because wherever you're at, so for example, you're going to have a minima for ES, you'll have one for EP. If there was an in-between, like an EX or something like that, then you'd have another transition state going to another minima, and then transition state going to the next one, and so on and so forth. Okay. We discussed briefly about the two relatively extreme cases where you have the lock and key, which really is easy to discredit right offhand, because if the substrate was like the key and the enzyme was the lock, and they were so complementary with respect to each other, then you would never get product. Then the substrate would go in, bind, everything's nice and happy on the inside, so why would it ever be broken apart, or why would you ever want to make another product? And so that can't be quite true. Then there's this idea of an induced fit model, which is where you bind the binding site for the substrate isn't completely complementary. So whenever it goes in and binds, it induces a conformational change, which results in a complementary fit. We're going to actually find out that that's a better explanation of what happens, but even in of itself, that's not 100% accurate, usually at least. Okay? And so this is the overall, just a second before. This one up. This is an overall figure from the book, but I would like to break it down, perhaps. So that way we can see it better. Okay? So they said, just imagine that you have, and it's relatively simple to imagine a reaction where you're breaking something from one large piece to two different pieces, like a protease, which is just an enzyme that breaks down proteins. Nuclease, which would be an enzyme that breaks down. What do nucleases break down? It's a family of enzymes that break down what? Nucleotides, nucleic acids. So technically in RNase, ribonuclease would do RNAs, DNase or deoxyribonucleases would do DNAs. But yeah, they just take something larger and they break them apart. Okay? And so if we just picture it, and I don't know why they said to picture it as a metal stick, but they have a metal stick. Then what happens is you can imagine a transition states where you have it bent, and then finally you can break it in two, and you've got your two pieces. And so that's why we have our substrate. It takes energy to bend it, and then you get your products. Okay, that's without any enzyme. Well, the point here is if it was perfectly complementary. This is what I was trying to imagine, and now this is where they're just throwing this idea. Oh, you got magnets. Well, but what does that mean? If it's perfectly complementary, you can imagine then that not only does the binding site look like the substrate, but for example, if you can imagine that if there were negatively charged, what they're trying to say here is if there were positive or negative charges here along this ES, you could have complementary positive and negative charges along the binding site there, or if it was a hydrophobic region, you could have a hydrophobic region on the enzyme. And so then what happens is, energetically speaking, this is what this is trying to show, and hopefully you can start to get an idea of being able to read the logic behind these energy diagrams. But it's so perfectly complementary that it stabilizes the ES. So now the ES complex is actually lower in energy than the substrate or the product for that matter. Okay? So what happens is originally, and I'm going to make these numbers up, but for example, we could have originally only taken, like maybe 20 kilojoules to get up that first hill, but now this is so complementary that it's an even bigger hill than what you started off with. And so that's why the lock and key doesn't really work. Okay. Now this one's assuming that the ES complex was lower than the EP, but in reality you could also have something that looks like this. This is also bad. So here's our our E plus S. So I'm just going to put the S there and the P here. You could imagine, though, and this is uncatalyzed, but what happens is if it was too complementary, something like this, then this is also bad. Okay, even though this ES complex here isn't, I was trying to draw it to where it's not, where it's higher in energy than the P, the overall hill that it had to climb to get up there was bigger than the first hill. So that's why that would be bad. Even though this one's not as low as this one, this ES complex isn't as low as the free product, it's got to get over a bigger hill than initially. And so that's why we have to look at how big of the hill, the quantity of the energy for each of these steps, okay? All right. So this is an idea where instead, it's even called transition state theory. I don't know if your book uses that term or not, but transition state theory is the idea that what happens is the binding site or the enzyme is that once the substrate gets in, it's not so much that it induces a conformational change only on the enzyme itself. I mean, it still can, but the binding site, or what the enzyme does best, is it makes it more likely makes it happier for the transition state. Then you already can imagine this is bound, but now it makes it even easier to bend it, so you're halfway there already, and then which makes it even easier. In doing so, it makes it easier to break. So that's what this is trying to show down here. Now it shows the ES and the S being exactly the same in energy. That may be true, but it doesn't have to be true. The important thing here is the fact that the transition state itself is lower in energy. And so this overall hill, so we have to add a little bit of energy to get the substrate to bind, but this hill for the catalysis to occur is actually smaller than the original big activation energy, and then you get the product. But this isn't the only one that's available, that's possible. You can imagine, which is sort of like what the quiz was going over, the whole idea here, is what happens if we had something that looks like this. First of all, there's the uncatalyzed. So there's S and P. But you could imagine it is fine, and sometimes it's possible to have ES. Okay, so I'm going to go through and label everything. You first get binding, then you get catalysis, and I did this deliberately, because then what you notice is I just wanted to point out it's possible to have a Michaelis complex or an ES complex that's lower in energy than substrate, but higher in energy than product. And I mean, I did this one. EP could be higher or lower. It doesn't really matter. It's all relative. I want to point something out here. So remember, the overall mechanism was this. It was binding to make ES goes on to be EP. That's not too shabby. I actually kind of spaced it out about right. That's a first. Okay. So if we look at this, and I'm going to call this step 1. And step 2, because there are 3 steps in step 3. First step is binding. Second step was catalysis. In the example that we were using before, was breaking the little pieces, breaking it to 2 pieces. And the third step is product dissociation. It's the product leaving the enzyme. In this little picture here, so we have substrate, you have to put in some energy, you get ES complex, so it's now bound. You have to add a little bit of energy in order for catalysis to occur. So you get the EP. Then you have to have energy in order for the product to leave. Which step 1, 2, or 3, is the rate limiting step for this mechanism now? Yes, it's 3. Step 3 is EP to E plus P, and that's because that's the biggest hill. And this is true. Sometimes it's not always going to be the chemical step. Sometimes they call it the chemical step, being the rate limiting step. It could be. It could also just as easily, for some enzymes, when you're starting to write your paper, you may find out that sometimes it's the binding step that's the rate limiting step. Or it may be some third or fourth step that's in the middle there. Or in this instance, I'm just showing an example where the last step, product dissociation, is a rate limiting step. In this instance, what it means is that the product really likes to be bound to the enzyme, and so therefore it makes it a little bit bigger. But overall, it's still going to be faster than the uncatalyzed reaction. Because the uncatalyzed reaction, you had to have roughly that amount of energy to get over. The biggest energy difference is this one right here. So now it's smaller. And one thing I want to point out, once again, you speed up, not only do you speed up the forward reaction, but you speed up the backwards reaction by the same rate, by the same magnitude. And because that hill going backwards is just as lowered as it was going forwards. So, my grandpa, back when he was alive, we talk about the good old days, and he would always, this is back in the, well, I'll use the English words here, but this was back in the days with the, what's the word, like the sticks, way back in the country. And so, he would talk about how back then that they had to walk. There was just a one-room schoolhouse, so they have to walk. And he'd say, we'd walk, barefoot, in the rain and in the cold or the snow or whatever. He goes, and it'd be uphill both ways. And I was kind of a little smart aleck kid. I was like, Grandpa, what were you doing wrong? How could you go uphill both ways? Something was going wrong, right? You're going to be going downhill one way. So that's the same thing here. It's the same principle, is that you're going to lower this overall rate by the same amount, by the same magnitude, both forward and backwards. All right, so this is just an example here, just to show. This is the catalase reaction. So it's just the breakdown of hydrogen peroxide to water and oxygen. It does happen normally on its own. So they give it a relative rate. Okay, you could use platinum. If you think back to organic chemistry, remember we talked about how they would use platinum as a catalyst. And it does decrease the amount of activation energy, and it increases the overall rate 10 to the power 4. However, our bodies have an enzyme called catalase, and catalase actually increases the reactive rate almost 10 to the power 9 more. So 10 to the power 8 more than the uncatalyzed reaction. Okay, so that's why whenever they say these arbitrary units, I really hate it. It makes it sound much more difficult than what it is. The way that they figure that out is they literally they say this is the rate. So for example, now we're always talking about, remember these are little k's for kinetic rate constants. So what you do is you take the rate whenever it's catalyzed, and you divide it by the rate that is, or actually here they're going to do the opposite. It doesn't really matter. Oops, let me go back. Take the rate, because they got big numbers, so they take the rate when it's uncatalyzed, and they divide it by the rate constant whenever it was catalyzed, and that's where they got this relative rate. They say, arbitrary units and blah, blah, blah. Yeah, that just means that they took, before it was slow, you divide it by, now it's much faster, and you're going to get a big number. That's all that they're meaning right there. Here are some examples of different rate enhancements. So you can see that you can get these quite enhanced. So you're going to find out about some of these enzymes next semester in greater detail. We don't cover cyclophilin. We do cover carbonic anhydrase. In fact, we've already talked about it a little bit already, in the sense that carbonic anhydrase is involved in the pH of your blood, right? Because it's one that actually converts bicarbonate and carbon dioxide. This is a big one. This is TPI, triose phosphate isomerase. Knowing what you know so far, what kind of reactions do you suppose an isomerase does? What's it going to do? Because you needed to know your enzyme families. What does an isomerase do? change from one isomer to another. And what this tells you is, we haven't covered sugars yet, but this is a sugar that has only 3 carbons, and it has to have at least 1 phosphate on it. And all this does is it moves where that phosphate is from carbon 2 to carbon 3, okay, and so, or vice versa. This is a carboxypeptidase. We're going to see that, oh, and by the way, that's in glycolysis and some of the other sugar carbohydrate metabolic pathways. Same thing with this one. This is a transferase, which means it's going to do what? It's going to transfer one group between one group from one thing to another. And then urease is a special named one, which is involved in the, which we'll talk about later on with in nitrogen metabolism. So it should, I don't want to spend hardly any time on this, in the sense that it should make sense that as you increase temperature, you're going to increase rate until you get to a certain point. And then it's going to be detrimental. And the reason why is it's going to start to denature the proteins or the enzyme, or the nucleic acids if it's nucleic acid based. But yeah, things are going to start to fall apart. So it's going to go slower. Okay, so that's why it should make sense. And so sometimes they call this T optimum or T max or something like that. I hate to say TM because that's the thermal melting temperature, which is related but not quite. That's just literally the temperature at which half of the protein would be falling apart, or half of the nucleic acid would be bound or unbound. So they call it TM for the thermal melting, so versus Tmax. Okay. I've already been mentioning these terms, ES complex. Okay. But there are many different things. They use binding energy a lot of times to form this. You could have other types of energies overall, and if you ever get the chance to take enzymology class or kinetics course, then we cover that in greater detail. Many times, but not always, you can have a transient covalent interaction. The important word here is it's transient because it's got to be reversible, or otherwise the enzyme is being consumed. So maybe the enzyme makes a covalent bond to an intermediate, and then it releases it later on. So that's why it's called a transient covalent. But it doesn't always have to be a covalent interaction. There's many enzymes that all they do is they help bind it in the right orientation to make it more likely for the nucleophile to come in and smack it around. Right. So other general terms that I wanted to go over for catalysis. So there's general acid, general base versus specific acid, specific base. Okay. So what this means, and this is probably, if I remember right, given many of your enzyme topics, this is probably the predominant type of catalysis that most of you will be talking about. So for example, a lot of those of you who are looking at the proteases, where you have like a serine protease or something like that comes through, it uses some type of general acid, general base, and it uses a covalent catalysis. Okay, so it doesn't have to be mutually exclusive. Okay, covalent obviously means it forms a covalent intermediate, but once again, it has to be reversible. General acid, general base means that you're going to use the side chain of an amino acid usually to make the nucleophile more nucleophilic, or to make whatever's being attacked more of an electrophile, make it easier for it to be attacked. Okay, now specific, what that means is literally it's a proton or a hydroxide ion that's being transferred using only water. It happens some, but almost always we're talking about general acid, general base. This is just an example. Okay, I don't want to draw the entire, but there's the backbone. Okay, this is just one example, and I forgot a linking carbon. And you don't have to draw this out, because you're going to see this mechanism later on. But I just wanted to show what I meant by general acid, general base. So what amino acid is this one? There's the backbone. It's within a protein. It's aspartate. Okay, and it's going to be acting like a general base right now, because what's going to happen is it's going to reach out, swipe that hydrogen, so it's acting like a base. And that's why it's called general base, because it's not specific, it's not hydroxide, but it's going in and it's taking that proton. Okay, what's the amino acid that it just took the proton from? That's histidine. And then what happens is these two electrons here can go boom. Sound effects optional. These two electrons here can then, in the double bond, can swing out and smack this, for example. And then, well, if this was a serine protease, which this is supposed to be part of serine, it can then make this oxygen more likely to go and attack something. I wanted to point this one out because this histidine here is both a general acid and a general base. See, this side of it is general acid because it's donating a proton. This side is going to be acting like a general base because it's taking a proton. So that's why you don't usually have just a general acid base catalyzed. Because doing the reverse, it's the exact opposite. Then this side is going to take the hydrogen back, so it's going to swap over, and that's going to take the hydrogen back, and you're going to get your carboxylate at the end. And so even though the aspartate started off as a general base, it may end up being a general acid for the reverse reaction. And then finally, one that we will cover in more detail later on throughout both semesters, and some of you may have this in your enzyme that you're talking about, is a metal ion catalysis. And that's where the metal ions help make something more nucleophilic, or that they are really important in holding either the substrate or the nucleophile or something in the correct conformation, the correct shape, in order for the reaction to occur. Okay. This is just a really quick review. Because I'd like to really get started today on Michaelis-Menten. So we're a little behind. But this is just from Gen Chem. You know, you have reactants, they go on to make products. So we always have the rate, which many times we say rate is equal to, I know in Gen Chem they liked V, or actually they may not, I don't know when you took it, but V. Sometimes they use the Greek letter nu, which kind of looks like the curvy V, like the cursive V. Either is fine, it's for velocity. We typically don't say rate. We almost always, in biochemistry, we'll use either the nu or the letter V. You can either do it in terms as a change of the concentration of A with respect to T or B. And since they're disappearing, it's going to be negative, right? Because the change is going to be negative. Whereas, or you can look at it as the formation of the product or products, if you have more than one, and it would be positive overall. Okay? Now, one thing is that's going to be different in biochemistry than Gen Chem is they like to use calculus more. So what this is, and I will probably be interchanging, this right here, which everybody seems to be, not everybody, but a lot of people, you know, when you see that big triangle concentration of P, triangle concentration of T, what does that really mean? It's the change of the concentration of P as the time changes. Well, that is a derivative, so that becomes dP dt. That's the exact same thing. It's just they use the lowercase d. I don't know if whenever you took calculus they ever explained that to you, but from Gen Chem, that big, or biology or whatever it is, they like to use the capital delta, and in calculus and a lot of the biochemistry texts, they use that lowercase d. Okay, and so lowercase d. Yep. All right, it said it right. All right, so that's why if you see that interchangeably, or if you start reading your textbook and all of a sudden they got little dp, dt, all that kind of thing, if you need to, you can even take it out and draw in triangles if it helps you. It's the same thing. All right, then if what happens here is you have the rate, or V, is always equal to every single step. If you remember the Gen Chem, there's always the rate constant, and it must be lowercase. It cannot be capital K. It's got to be a lowercase k, and you got to make sure it's really obvious. A capital K is an equilibrium constant. Okay, that means what that tells you is the extent with which a reaction occurs. How much product versus how much substrate you'd make if you had a gazillion years. It doesn't give you any idea about how quickly it goes. Lowercase k's are rate constants. They give you an idea how fast something goes, but they don't tell you how much product or how much substrate you'll have in the end. The two k's, capital and lowercase, are related to each other, and we'll talk about that a little bit. But once again, they are related, but the big K is a ratio of little k's. And so once again, make sure you do little k's every time we're talking about how fast something is going or how slowly. Capital K's means the overall equilibrium constants. So it's a thermodynamic number. Okay. And then we have a concentration. You have some type of exponent, which is called the order of the reaction. So for example, this would be first order with respect to A, first order with respect to B, because it's both to the first power. But overall, it's second order, because 1 plus 1 is 2. All right. And so, yeah, this is a specific example. All right, so it is possible to have a zero order reaction. That means it's a constant rate. No matter how much substrate you keep adding, it will never go any faster. So it doesn't depend upon how much reactant that you have. And I'll talk about what this means right here in just a moment. We've already talked about S, an active site. This is the enzyme substrate complex. Right, so I just go on. Okay, so let's start looking at a specific example. This is aspartate transcarbamoylase, or ATCase, which is a mouthful. By the way, what functional group is this right here in red or pink, whatever that color is? What functional group is that? It's an amide, right? Because you have a carbonyl or acyl group and a nitrogen and amine. Whenever it's by itself, if you remember, like acetyl, when we talk like acetic acid or acetaldehyde, remember acid means two. Well, whenever it's just the acyl group and the nitrogen here, that's called a carbamoyl group. And the reason why I mentioned that is because next semester we talk a little bit about carbamoyl transferases, and that literally means it just transfers an amido group, an amide. Okay, so that's carbamoyl phosphate. This is aspartate, and it's going to make carbamoyl aspartate, okay, which is just one of the steps to make DNA or RNA. It's a much more complicated metabolic pathway overall, but this is the first step. Okay, so this is the enzyme that does that. So, what happens here, and there's a couple things I wanted to point out, is at really low concentrations of substrate, and then now we're going to start talking about how fast the reaction velocity, what the velocity is. Really low concentrations, of course, if there's no substrate around, you won't have any, so it should be 0. But at really low concentrations, and it starts to get faster, but at some point in time, it's actually 0 order, because no matter how much more substrate you add, it will never get faster. What that means is that all of the enzymes there are bound. All of their binding sites are used up. So you can imagine if you have a car company, I should say. Let's say like Ford. You know, they have their assembly lines and everything that's going. And so you can imagine at first if you only have a handful of parts or a handful of people there working on it, it can only go. It goes slowly. Then if you add more people and more workers there, it's going to go faster and faster. However, at some point in time, all the assembly lines are full. And so, therefore, you can keep adding parts, as many parts as you want to. Your car company's not going to be able to make any more because it's completely full. All the binding sites are full. Same thing happens with enzymes. Okay? So that's why where it reaches technically, it's the asymptote. If you think back to, was that calculus or calculus, the asymptote that it approaches, where you get that 0 order, that's called Vmax, or maximum velocity. So this is Vmax. And we'll never get any faster than that because everything is bound. Now, if we think back, what does it mean when this is sigmoidal? You can kind of see it's not hyperbolic. It's sigmoidal. What does that sigmoidal shape indicate? It's allosteric. Remember, it's also called cooperativity. And so this one is, and that's really important because we cannot do what's called Michaelis-Menten kinetics, steady state kinetics, on something if it's allosteric, okay? Because it's more complicated than simple terms. But once again, that just means that there is allosteric. We're going to find out there are lots of effectors that affect ATCase. Some of them will make it faster, and some of them, will make it slower. Okay, so the sigmoidal shape means that it's allosteric. It has a cooperative binding like hemoglobin. But this is a generic curve, right? I added a couple points in. Ooh. So this is zero order, right? Because we have our asymptote that is approaching. So that's Vmax. Now, what some of the books will state, and we're looking at initial velocities, and I'll explain that on the next class why that's important. Some books will tell you right here, oh, this is first order. As substrate binds, it's first order, and then it goes to zero order. I just wanted to let you know it's not always going to be first order. Like the one that we just saw, the ATCase, that wasn't first order because it's sigmoidal. Okay, but it is true for anything that follows what's called Michaelis-Menten kinetics, which is a fancy term for steady state. Okay. And I'll explain what that means by steady state kinetics starting on Wednesday.